All right, buckle up, because today's deep dive is going to stretch our brains a little bit. We're tackling space-time.
Yeah, no way around it. It's a mind bender.
Definitely. But we're tackling it head-on with, and get this, excerpts from the Feynman lectures on physics.
Classic.
Right. Specifically, Chapter 17.
Yeah.
It's all about space-time. And lucky for us, Feynman was a master at explaining these wild concepts in a way that, well,
Almost makes sense.
almost the key word.
Exactly. So our mission today, if you want to call it that, is to take what seems like crazy, complicated physics and see if we can make it, I don't know, a little less intimidating, maybe even kind of fun.
Fun is good.
Well,
Always a good goal.
Right. So to get us going, Feynman starts off with this really simple question about, get this, depth. Like how deep something is. Ever notice how when you walk around an object, the way you see its depth, it changes?
Sure, you get a different angle on it, a different perspective.
Yeah, exactly. You're seeing different sides, different aspects of its depth. And that's actually a really profound point that Feynman's making.
Well, we tend to think about depth and width as being totally separate things, right? Like they're just different measurements. But what if they're not? What if they're just different ways of seeing the same thing, depending on where you are in space?
Okay, I see where you're going with this.
And that's where this whole space-time thing comes in. Because just like moving around an object changes how we see its depth, moving really, really fast, like close to the speed of light fast.
Things get weird.
Things get weird.
Yeah, relativity kicks in, Einstein's theory of relativity. And it tells us that space and time, well, they're not these separate absolute things we always thought they were. They're actually woven together, interconnected into this fabric, this unified dot thing called space-time.
Okay, so it's not just that objects take up space, it's like they exist across time too. Like they've got a whole history, a path they've traveled through both space and time.
Exactly. Think of it like this. Imagine a graph, right? Where time is going up and down, that's the vertical axis, and space is going left and right, that's the horizontal.
Okay, got it. A space-time graph.
Now, picture a parked car, just sitting there. It's not moving in space, right?
Right, it's parked.
So on our graph, it would just be a straight vertical line moving through time.
Oh, I see. Like it's timeline, just existing second by second. Makes sense.
Exactly. But what about something that is moving, like, say, a ball flying through the air?
Well, it wouldn't be just a straight vertical line anymore, would it?
Nope, it'd be diagonal, moving through space and time. And the faster it moves, the steeper that diagonal line gets.
Whoa, so the angle shows the speed.
Exactly. And here's the really wild part. Light. Always traveling at the speed of light, that would be a line at a fixed angle, a 45-degree angle.
Whoa, so even something as constant as the speed of light, it has its own special place in this space-time diagram.
It sure does.
Okay, I think I'm starting to see how this all fits together, but it definitely raises a big question.
And what's that?
Well, if space and time are all mixed up like this, shouldn't there be a whole new way to measure distance? Like a space-time distance.
Right.
Like our normal ideas about distance just kind of break down when you're talking about the fabric of space-time itself.
Exactly. And that's where the super interesting concept comes in. Intervals.
Intervals? Okay, gotta admit, not a term I use every day. What's that all about?
So in space-time, an interval isn't just about the distance between 2 points in space. It's about the, how to put it? It's about the space-time distance between two events.
Events, like happenings.
Yeah, exactly. Like a firecracker going off, that's an event. Or you snapping your fingers, another event. So an interval takes into account not just how far apart they are in space, but also how far apart they are in time.
Okay, so it's like a more, I don't know, a more complete way of measuring how separate two things are, considering both space and time.
Exactly, you're getting it. And here's where it gets really wild. Unlike distances in our normal 3D world, intervals in space-time, they can be, get this, real or imaginary.
Hold on, imaginary. I thought we were talking physics here, not like fantasy novels.
Haha, no, it's still physics, I promise. But it's one of those things that shows just how different space-time is from our everyday experience. Think about it like this. Let's go back to our space-time graph, right? Imagine two events. Call them event A and event B. If you can draw a line between those events, and that line stays within that 45-degree angle we were talking about, the one made by the path of light.
Okay, I think I'm picturing it.
That means, in theory, you could travel between those two events at a speed slower than light. And that kind of interval is called a time-like interval.
So time-like, meaning it's a measure of events that could actually be connected, like one thing could actually influence the other.
Yeah.
Because, information could travel between them.
Exactly. You nailed it. Now, Those imaginary intervals I mentioned, those are called space-like intervals, and they happen when the line connecting your two events on the graph, it falls outside that light cone.
Light cone.
Yeah, sorry. It's just what we call that cone-shaped area on the graph that represents all the paths light could take from a single event.
Gotcha. So space-like intervals, that's when things are so far apart in space or so close together in time that you'd have to travel faster than light to connect them.
You got it. And because nothing can travel faster than light, at least as far as we know.
Right, Einstein's cosmic speed limit.
Exactly. So those space-like intervals, they represent separations that are just, well, too far apart for any kind of influence to travel between them. They're kind of in their own little bubbles of space-time.
Okay, so time-like intervals are within the realm of what's possible, at least in terms of cause and effect, and space-like intervals, they're like off limits.
In a way, yeah. It's like the universe has drawn these boundaries, these limits on what can influence what, and it all comes down to the speed of light.
That's wild. It's like a cosmic web of cause and effect, all neatly defined by this ultimate speed limit. And it really makes you think about, like, the nature of now, what we perceive as happening simultaneously all around us.
It's not so simple, is it?
Not so simple at all.
Our everyday intuition about now just kind of breaks down when you start thinking about the vastness of space and the fact that light, well, it takes time for light to travel.
Right, it's not instantaneous. So you're saying what we think of as now, it's not universal.
Not at all. Let's take a concrete example. Alpha Centauri.
Okay, Alpha Centauri, that's the closest star system to us, right?
Exactly, about 4 light years away.
So when we look up at Alpha Centauri at night, we're actually seeing light that left there 4 years ago.
Precisely. Which means if we could somehow see what was happening on a planet orbiting Alpha Centauri right now, this very second.
We'd be seeing 4 years into the future.
In a way, yeah. Because that light, the light that would show us what's happening there now, it hasn't even reached us yet. It's still on its way.
Whoa. That is seriously mind-blowing. So we've established that space-time is this crazy intertwined thing, and that intervals are our new way of measuring the, distance, so to speak, between events in this weird new landscape. But how do we actually work with this stuff? I mean, how do you even begin to do calculations in a world where space and time are all mixed up?
Yeah, it's like, I get that the rules are different in space-time, but how do we actually use those rules?
Well, let's think back to our old pal, classical physics, for a sec. Remember vectors?
Vectors, you mean those little arrows they're always drawing in physics class?
Exactly. Those arrows, those vectors, they're a really handy way to represent something that has both a size, like how strong it is, and a direction.
Right, like velocity.
Yeah.
The arrow tells you how fast something is going and which way, or force, how hard it's pushing or pulling and in what direction.
Precisely. Vectors were, and still are, super useful for figuring out how things move, how forces work. Get this, in space-time, we've got something kind of similar. We call them 4 vectors. 4 vectors. Okay, is that like vectors, but with an extra dimension for time?
You got it. Just like regular vectors helped us understand motion in space, 4 vectors, they help us understand this relationship between energy and momentum, but in this unified space-time we've been talking about.
So instead of thinking about energy and momentum as 2 separate things, we're kind of combining them in this 4-dimensional way.
Exactly. And here's a real head trip. One of the big aha moments in relativity is that energy and momentum, they aren't actually totally separate things. They're like 2 sides of the same coin, intertwined, just like space and time.
So the energy something has and the way it's moving through space, it's all connected in this 4-dimensional picture.
Exactly. Think of it like, I don't know, looking at a map, a flat map, and then boom, you see it in 3D. Same landscape, but a whole new level of understanding.
Okay, that's a cool analogy. I get the elegance of it, but what are the practical implications? What can we actually do with these 4 vectors?
Well, for one, they give us a much deeper understanding of some of the most fundamental laws in physics, conservation laws.
Conservation laws. You're talking about like conservation of energy. Like energy can't be created or destroyed, just transformed.
Exactly. That's one. And then there's conservation of momentum, the idea that the total momentum of a closed system always stays the same.
Right. I vaguely remember those from school. But how do 4 vectors change things?
Well, in relativity, it turns out those 2 separate laws, conservation of energy and conservation of momentum, they're actually part of a single, even more fundamental law, the conservation of 4 momentum. It's not just that energy and momentum are conserved independently, it's that their combined 4 vector remains constant, even when things are whizzing around at close to the speed of light.
Wow, so it's like this beautiful, elegant unification of these core principles,
Mm.
all thanks to this idea of four vectors.
Exactly. And it gets even better. You know what else fits perfectly within this framework? Light.
Wait, light. But light doesn't have mass, right?
You're right, it doesn't have rest mass, but it's always in motion, always traveling at, well, the speed of light. And it turns out that its energy, which is related to its frequency, is also directly related to its momentum.
So even though it's massless, light still has momentum. That's wild.
It is. And it fits perfectly within this four-vector description. It's like the ultimate confirmation that we're on the right track.
This whole deep dive has been incredible. Seriously, it's changed how I think about, well, reality. That space and time are so interconnected, how energy and momentum are linked at this deep level. It's amazing. If we had to, like, sum it all up, what would you say are the biggest takeaways here?
I think the biggest takeaway is just how limited our everyday experience of the universe really is. We experience this tiny sliver of reality, but underneath it all, there's this much grander, more interconnected reality playing out, this four-dimensional world where space and time are woven together.
It's humbling, and kind of awe-inspiring at the same time.
Absolutely. And it leaves us with some pretty profound questions, too. We've talked about objects existing as these, like, blobs across space-time, stretching across both space and time. What does that mean for our idea of free will? If our paths are already laid out in this four-dimensional tapestry, do we really have a choice in what we do?
Whoa. That's a question to sit with for a while.
For sure.
Well, I know I've got some thinking to do. This has been an amazing journey. Thanks for being our guide through the wild world of space-time.
My pleasure. Always happy to warp some minds. Keep those brains bending out there, everyone.